Welcome to Data Science Experience and our first video for the exploration of the binomial distribution. The binomial distribution is an important statistical tool used to determine the probability of observing a specified number of successes across a fixed set of independently observed trials, each with a binary outcome of success and failure. It provides a clear framework for the quantification of uncertainty in binary trials and is useful in real-world applications from clinical trials to quality control in manufacturing. The binomial distribution models a discrete random variable x that counts the number of successes in independent trials gathered through sampling with replacement. Each observation in the trial has a constant probability of success. Breaking this out, we have a selection of samples for a discrete random variable. Each represents a discrete observation because individual observations or trial selections must be evaluated, and a partial observation is not possible. By sampling with replacement, the probability of each observation being selected remains constant across selections in the trial, ensuring independence. If sampling without replacement were performed, the probability of each individual observation being selected would increase as each selection was drawn, reducing the independence across trial selections. To qualify as a binomial experiment, 4 conditions must be met. First, there is a fixed number of trials represented as n, the sample size. This is predetermined through statistical calculation in advance of the experiment. Second, as discussed previously, sampling must be performed with replacement to ensure independence of observation. Third, the outcome of each trial must be binary, generally referred to as success versus failure. Fourth, the probability of success must be a constant for each trial. Collectively, these are more technically referred to as Bernoulli trials, which are identically distributed and independent events with binary outcomes. There are many purposes for using the binomial distribution. It allows for inference of exact probabilities for discrete outcomes, can be applied to any binary outcome scenario with fixed trials, and provides insight for testing the statistical significance of a result. The equation for the binomial distribution is complex, but can be broken into its modular components for a plug-and-play calculation where each variable is defined and input. With the binary distribution, represented with a binomial probability mass function, the probability of achieving k number of successes across n independent trials with a fixed success probability of p is the combinatorial expression n choose k multiplied by p to the kth power, again multiplied by 1 minus p raised to the n minus kth power. Settling n choose k results in a factorial function. This calculates the probability as n factorial divided by k factorial times the factorial of n minus k. This result is then multiplied by p to the kth power, which is then multiplied by 1 minus p raised to the n minus kth power. In this function, x represents the number of successes for which the probability is being calculated. P represents the known probability of success for each trial, n is the predetermined number of fixed trials, and p of x equals k is the probability of k successes in n trials. Within this function, each factorial, denoted as an explanation point, represents the product of a positive integer and each integer below it down to 1. For example, 5 factorial is calculated as 5 times 4 times 3 times 2 times 1 equaling 120. Let's review an example where a binary distribution would be used. Good Living Pharmaceuticals is testing a new drug therapy believed to have an increased efficacy of 75% over the prior drug, which had an observed cure rate of 60%. First, determine the number of patients that must be enrolled to detect the improvement at a significance level alpha of 0.05, calculated as 1 minus the confidence level, and the beta value of 0.20. This beta value is a common benchmark in clinical trials, representing the probability of failing to reject the null hypothesis that there is no statistical significant difference in the two therapies. Power, which represents the probability of correctly detecting a true effect, is 1 minus beta. Second, using the calculated sample size, determine the probability that exactly 59 patients were cured, assuming the rate continues at the previous 60%. Third, again using the calculated sample size, determine how likely the cure rate is for exactly 59 patients, assuming the efficacy does increase to 75%. For the first question, the number of patients n that must be enrolled in the trials is calculated. This is calculated using two standard terms for clinical trials known as alpha and beta. The problem has provided standard terms of a significance level of alpha equals 0.05, which is calculated as 1 minus a confidence level of 95%. Alpha represents the probability of what's known as a type 1 error, where the null hypothesis of no statistical significance is incorrectly rejected when it is actually true. Next, the expected probability of failing to reject the null hypothesis when the alternative of statistical significance is true is set at 0.20. This is the critical value from the type 2 error risk. Beta corresponds with power, or probability of correctly detecting a true effect, of 1 minus beta, or 80%. This is a standardized value corresponding to the desired statistical power used to ensure the test can detect a true effect. The calculation for the fixed trial size is complex, but, similar to the binomial distribution itself, is a simple matter of filling in the input variables from available information. The equation for n is equal to the square of the sum of two terms. First, the standardized z-statistic of a two-sided test at 1 less alpha divided by 2 is multiplied by the square root of the original probability, p of 0, multiplied by 1 minus the original probability. Second, the standardized z-statistic at 1 minus beta of 0.20 is multiplied by the square root of the new probability, p of 1, times 1 minus the new probability. This square term is then divided by the square of the new expected probability minus the original probability. Filling in these variables, we again have the square of the addition of two terms. First, the standardized statistic of 1.96 multiplied by the square root of the product of 0.60 and 1 minus 0.60. Second, the standardized statistic of 0.84 is multiplied by the square root of 0.75 times 1 minus 0.75. This squared addition is divided by the square of 0.75 minus 0.60. Using 5-up rounding to no digit because a sample count must be a discrete integer, it is determined that the trial must consist of 78 observations. The second question uses the fixed and predetermined trial size of 78 from question 1. It poses the scenario of what the probability is that exactly 59 patients were cured, assuming continuation of the original cure rate of 60%. This is where the binomial distribution comes into play. We are able to calculate the probability of x being exactly 59 observations. From the provided information, n has been calculated as 78. The probability of k equaling 59 is being determined, and the known cure rate of p of 0 is 0.60. Using the defined equation results in the formula of 78 factorial divided by the product of 59 factorial and the factorial of 78 minus 59. This is multiplied by 0.60 raised to the 59th power, and the result is multiplied by 1 minus 0.60 raised to the 78 minus 59th power. This calculation results in a value of 0.0015, meaning that there is a 0.15% probability that exactly 59 patients will be cured if the efficacy rate remains at 60%. This calculation focused on a single exact outcome where the probability of 59 of 78 patients being cured was determined. Probability calculations with the binomial distribution can also be performed to determine the probability of being at or below a fixed value, such as no more than 59 patients being cured. The alternative can also be calculated, the probability of more than 59 patients being cured. The third question again uses the fixed and predetermined trial size of 78 from question 1. However, this changes the scenario to the probability of exactly 59 patients being cured, assuming the efficacy rate increases to the expected 75% from the original 60%. The probability of x being exactly 59 is determined through the same process, with p of 1 of 0.75 being used in place of the p of 0 of 0.60. Therefore, from the provided information, n has been calculated as 78, the probability of k equaling 59 is being calculated, and the expected cure rate of p of 1 is 0.75. Using the defined equation results in the formula of 78 factorial divided by the product of 59 factorial and the factorial of 78 minus 59. This is multiplied by 0.75 raised to the 59th power, and the result is multiplied by 1 minus 0.75 raised to the 78 minus 59th power. This calculation results in a value of 0.1038, meaning that there is a 10.38% probability that exactly 59 patients will be cured if the efficacy rate increases to 75%. This visualization displays the binomial probability mass functions for the two cure rates evaluated previously. The x-axis is the number of patients cured, while the y-axis is the probability of observing that exact number of cured patients. The orange bars shifted to the left represent the probability of each fixed number of cured patients based on the original 60% rate, while the blue bars shifted to the right represent the 75% rate expected with the new drug. This right shift indicates that greater numbers of patients have higher cure rates than for the original distribution. The 75% cure rate also shows higher peakiness and greater concentration around the mean than the 60% cure rate, indicating higher probabilities of success with decreased variability. The binomial distribution provides a framework for evaluating discrete outcomes with the binary result of successes and failures. It can be used to calculate the likelihood of a specific number of successes in fixed trials, or to provide the likelihood of at least that many or more than that many successes. This provides a determination based on probability theory and statistical reasoning. Binomial distributions are commonly used in medical trials testing for efficacy, fraud detection and banking, spam email filtering, retail product returns, and manufacturing and production realms, especially in relation to destructive testing. This has been the Binomial Distribution by Matthew C. Vanderbilt at Data Science Experience.